about using LINBIT SDS with OLVM. Before I start into the topic, let me state what we are solving here. So our part is that you have a number of physical nodes containing physical storage devices, and this software turns that into a highly available cloud storage for your virtual machine images and ISO images, etc. So I'm doing a top-down approach today, and the topmost software component is called LINSTOR. And let's start here with an overview from the architectural point of view. So the LINSTOR software is a distributed system. It comes with two main components. One is the LINSTOR satellite that runs on every node of the cluster. It's configurationless, stateless. You install it, that's it. The other part is the LINSTOR controller that is stateful. So you have one instance of that running per cluster, and it has failover locations. The controller offers a REST API, and the controller reaches out to its satellites to do things there. And on top of the REST API, we have a command line interface, a GUI, and the whole system interacts with OLVM either as presenting an iSCSI target or being integrated more natively using a technology called Cinder or CinderLib. For smaller systems and for self-hosted engine, you will use the iSCSI part. For bigger installations, CinderLib makes a lot of more sense. Then let's go into the examples. So to explain how all this works, I'm looking at a sample cluster of 6 nodes, and each of those nodes has enough CPU and memory to run the actual workload, and it also has built-in storage devices. So might be NVMe drives, might be rotating Rust. When LINSTOR gets a request to create a virtual storage device for a virtual machine, it already knows where the virtual machine will run at first. So what it does is, and we are assuming here that our storage policy is that we want to have 2 replicas for purpose of failure safety, right? So we know the VM will start here, and we create 1 replica at the same node and 1 replica somewhere else for redundancy purpose. So same for the black VM. We have 1 replica here and 1 replica somewhere else. So this layout gives us top performance for all read requests because we can fulfill the read requests locally without creating traffic on the network, without adding additional latency for fulfilling those requests. But of course, VMs might move, right? Maybe it's live migrated to another node where we don't have a copy of the virtual volume. That's no problem. We access the content of the virtual volume over the network, so read requests are now shipped to these nodes. So this node has 2 possible storage nodes to go, so it will like do a load balancing of those read requests. Write requests, it always sends to both concurrently. And compared to the previous layout of the VMs and the storage locations, this is not the optimal layout, right? You can configure LINSTOR that it migrates storage to the compute. That's completely optional, but let's assume we have done it. And this runs here for an extended amount of time. That might be 10 minutes, that might be 24 hours, whatever you configure. And now LINSTOR checks out, okay, I have enough available storage capacity here in this node. So it will create a 3rd replica It will start the resync of all the data over to this node. And that's all completely transparent to your VM, right? The VM doesn't notice this. And after this resync is complete, it will remove the third replica because the storage policy was just asking for 2 replicas. So I hope this gave you an idea how this works. And I'm doing this top-down approach. Now let me talk a little bit about the low-level component, which forms the data path of the solution. And that's DRBD. And DRBD is a kernel driver, so it's in the Linux kernel. It presents your virtual block devices. Def DRBD is something. And such a virtual block device switches into primary role in the moment it gets opened. And in this case, it will be opened by the QEMU or KVM process when a virtual machine starts, right? If you would close it, it demotes the secondary, and a moment later, you can open it somewhere else. Then it will be primary there, and that determines the direction of replication. It can also do multiple physical storage volumes with different properties within a replication group that's called consistency group. So that's very useful if you use it with databases, and the database might have fast storage for its write-ahead log and maybe cost-efficient storage for the table storage. It is not a two-node technology. It can replicate to multiple nodes concurrently. Each of those replication links can be synchronous or asynchronous. You might switch that at runtime. And it also supports diskless nodes, which might be in primary role. So that means the application, the KVM QEMU process actually accesses it on a node which doesn't have a local replica. So in a way, you can think of it, it is like an iSCSI initiator that's connected to 2 targets concurrently. Now, what happens if something fails? Let's say we have a read request coming down from the VM and it's sent to this storage node, and the storage node crashes before it can fulfill it. Then DRBD on this side would notice that, reissue the read request to the other node, and fulfill it for the KVM process. When the crashed node comes back, it gets automatically reintegrated into the cluster as short resync happens, where this node sends the logs that were changed in the meantime. And now let's look at all that from another point of view. This is here, the orange box is like the operating system kernel, so the Linux kernel. And here we have this usual IO stack. And this is the position where DRBD inserts itself into the IO stack. And so you can see whenever a write comes down this path, DRBD sends it to the secondary node. It gets written there to the storage device. The acknowledgement travels back. And only if DRBD receives the acknowledgement from remote and the completion event from local, it will issue a completion event to the upper layers. What types of applications are our customers running on top of this technology? We see a lot of transaction processing. So all kinds of databases, Oracle database, and the open source databases. We also see it being used a lot for analytic processing, also databases. Sometimes I get the question how this is different from Ceph, right? And the difference is that this solution is really tailor-made for block storage. And with that, it is more efficient and delivers better performance. On the other hand, we don't do object storage, or it's not a distributed file system. So because we're so specialized, we have this in-kernel data path. We have a lot of optimizations in it. We decide in the moment you create a virtual volume on which servers we have the parts, the replicas of the virtual volume. We are building on existing components like DRBD, LVM, CFS, etc. And not only because we're lazy, but because your day two operation teams might be already familiar with some of these technologies, and it's not a huge black box for them. And the whole system is very well suited to be used in a hyperconverged way because it consumes very little CPU and memory resources for what it does and compared to alternative solutions. Here in the slide decks, I have a few pointers to benchmarks we published. So you can find here on our blog those papers. Okay, that's it from my part.